I'd like to thank everyone, Michelle, Charles, Michael, and Sergio, and the rest of KISS for having me. As a little matter of background, I've been at this Cubesat stuff since about 2000, when I was helping out at Stanford with Professor Bob Twiggs, who's one of the originators of the Cubesat standard. He kind of had the idea of how to make a small satellite that we would basically bring to a FedEx counter, pay FedEx, and the next thing you know, it'd be on orbit, and if it wasn't on orbit, FedEx would give you your money back. But anyway, the problem that he had was that each year, Stanford runs on a quarter system, each year the students would come in the fall quarter, look at what the students had done in the past, say, we don't want to do it that way, we want to do it our way. And they would get to a certain point, but not really reach critical mass in terms of having something ready for flight at a later date. And so he and I was helping to very peripherally teach a class that he was teaching, and he lamented that he just didn't have quite all these components that he wanted to be able to take the students to a final resolution, actually, to deliver a Cubesat. And so he sort of cajoled and persuaded me to put together eventually a proposal. I was well qualified to do this because I was currently, at that time I left my first company, but at my first company I had gained a lot of expertise in terms of building consumer products. I knew electronics, I knew software, I knew structures, etc. And to make a long story short, we put together this thing called NPD1, New Product Brief 1, which was a concept for a kit to build Cubesats. And we floated that on the internet in, I think it was November of 2000, and we just thought, the world was going to be a path to our door. And let me tell you, I was dead. Nothing happened for maybe a year, and then occasionally we get a ping from a consultant who was interested in Cubesats, what is this stuff, but still nothing really happening. And then about August of 2003, we got a ping from NASA, which is now JAXA, the Japanese Aerospace Corporation. They said they wanted to buy one. And our response was, well, that was almost 2.5 years ago. Things have changed very quickly within this market, embedded computing and all that. We need to reassess our proposal and get back to you. So my partner, who's still my partner at Pumpkin, Adam Reese, who's our chief mechanical designer, we sort of did a month-long retreat. We pretty much threw out everything we had done, except for the fact that our structure was made of sheet metal. And we came back to JAXA, and we said, okay, here's our current proposal, and you have to buy 3, and we thought we were really sick. We said they're going to be $2,500 a piece. And immediately, check, wire shut up the next day. So sure, that was in, let's say, August or September of 2003, and on December 31st, 2003, we shipped them 3 units. And that was the beginning of our foray into doing very small satellites. So what I'd like to focus on today is a couple items. I'm going to talk about Cubesats and these picosatellites or nanosatellites, depending on where you're coming from, how you want to call them. I want to give you an introduction and some overview of those. That's sort of more an engineering talk. I'll be frank. I think some of the speakers who are going to follow me are going to be focusing more on the science. I do tend to focus more on the engineering. I'm also going to be talking about what it means to be a designer in this space and the lessons that I've learned, and I hope to pass on to others in terms of addressing how one builds these satellites and good practices and all that. We're going to be channeling Jonathan Ive, who is Apple's chief designer. I gave a talk where I quoted a lot of the things that he was saying about design, and I'm going to try to get across to you why I think that listening to somebody from Apple, which is clearly a different market than what we're talking about, actually has relevance in this discussion. And then, in the end, I'd like to talk about some of the interesting areas that I think are coming up in the Cubesat realm and hold a lot of promise for greater mission capabilities. Okay, so let's just do a first overview of Cubesats. Basically, Bob Twiggs at Stanford had proposed the notion of this small satellite. It was originally in like a plexiglass box that was meant to hold Beanie Babies that he bought at Test Plastics. This sort of set the initial size of a 10 by 10 by 10 centimeter thing. I think initially it was probably 4 by 4 by 4 inches, and it's close but not the same as 10 by 10 centimeters. over at Cal Poly, Professor Fusari then formalized how this would actually be deployed into space. So this CubeSat would go into this P-pod. This is essentially a jack-in-the-box, a square-walled box with a door that pops open and a big spring in the back and just kicks the CubeSats out. And the P-pod was designed to handle 3 of these at a time. The standard is called the Cubesat Design Standard, the CDS. It's managed by Cal Poly. It used to be a few pages, maybe now it's a few tens of pages, but it's still pretty short, frankly. The critical element is basically that we're doing this keep it simple, stupid kind of mentality, 10 by 10 by 10 centimeters, and really very few additional requirements that you need to meet in order to satisfy their willingness to put one of your CubeSats in one of their P-pods. Important to note that while the standard essentially says that it's 100 by 100 millimeters, there's actually a little bit more room because normal to each face, you're allowed 6.5 millimeters of additional volume. So realistically, the largest aperture you can have, et cetera, is 113 millimeters. So sometimes you might see 100 millimeters, sometimes you might see people pushing it a little bit more. This is why they're able to do that. So it's a very simple standard. By being simple, it's managed to keep the cost relatively low. Now, let's talk a little bit about the generations as I see these. The very first CubeSats were essentially modern Sputniks. My company had a customer in Colombia, Universidad Sergio Arboleda, it's a private university in Bogota. They had a crew of about 9 people who had essentially no previous space experience. They bought one of our kits. About 2 years after they purchased it, well, actually, I got a frantic call from Cal Poly saying, Sergio Arboleda's CubeSat's here and it has some issues. So I went down there and I took a look at it and I thought, oh boy, that doesn't look good. First of all, I saw there was a little bit of damage in the corner that shouldn't be there. The other thing is there were no solar cells on. What is going on here? I see panels that are made to handle solar cells, but there are actually no solar cells on. And this was getting ready to go. So I eventually learned that there were some ITAR issues. The State Department found out that people were talking to the Colombians without the proper paperwork in place, etc. The Colombians were told they couldn't enter the U.S. for 2 years, but no one told them they couldn't send their satellite to the U.S. And so they did something very, very smart. They realized they had a launch date and they had to do something to make their satellite work. So what they did is they actually stripped every vestige of solar cells out of their satellite, packed it with extra batteries, made their launch date. I resolved that little damage issue that was there. And they launched, and they operated for 34 days as a modern Sputnik. It was a 2-directional comms, but I don't think the uplink ever worked, but the downlink did work. It beaconed for 34 days on the battery side. To me, that was a very object lesson in taking advantage of this very simple design mentality and actually getting something to work. Not re-scoping it so that there's additional things to make, but instead just keeping to that very original idea, very simple, essentially a modern Sputnik. And to this day, those guys are like heroes in Colombia because that was Colombia's first satellite. Now they're working on a different satellite. So there are several satellites along those lines. The second generation I consider to be the one that demonstrated that the 3U CubeSat has utility. Now I mentioned in the previous slide that the P-pod can handle up to 3 CubeSats, but it can also handle 1 CubeSat that's 3 times as long. So this is what we call 3Us, and especially DoD has really glommed onto the notion that the 3U is probably the one form factor within the standard CubeSat specification that is in fact useful. So as an example, in December of 2010, SpaceX put up the Falcon 9. There were 6 P-pods on that Falcon 9. There were in fact 8 CubeSats in those 6 P-pods. There were 4 CubeSats that were 1.5U in size. That was from Los Alamos. There were 2 CubeSats from the Naval Research Lab. There was 1 CubeSat from the Army. That was SMDC-1. And there was 1 CubeSat from Northrop Grumman. That was the only private one on board. All 6 functioned. It was fairly, as you recall, this was a test mission to do ISS resupply, so the orbit was pretty low. They all came down within 1 to 3 weeks or so. But nonetheless, they all worked, and the price of all of those was pretty reasonable. I would say that realistically, you were looking at, let's just say round numbers, 1 to 2 million per satellite. Plus, SpaceX has announced, I think their pricing is $397K for the launch itself. So 1.3K, 2.3K, 2.3 million kind of pricing for those. So we now sort of establish that the 3U is a very useful package. I feel that we're currently in the 3rd generation. We're seeing a lot more power available on the CubeSats. We're seeing attitude control, typically, and determination, typically in terms of reaction wheels and magnetometers, but we're going to see some other approaches as well, and propulsion. Propulsion is interesting, not only for attitude control, but also orbit changes and deorbiting as well. And then I think the 4th generation will essentially be constellations. Okay, so what are some of the challenges in CubeSat design? In my opinion, one of the biggest challenges is you're trying to pack a whole lot of stuff into a small space. Unlike, say, if you were putting together a microsat where you essentially can buy an individual standalone module bolted to the wall of the CubeSat and run some harnesses to it, you don't have that freedom when you're doing CubeSats. There's something too small. You have a much higher level of integration. And so that tends to complicate things rather than simplify them. You can very quickly run into volume problems. You have this much stuff that you need to put in a CubeSat, and in their current form factor, they're not going to fit. So you have to get very imaginative as to how you're going to be doing that. Also, the power has been pretty brutal. In the 1st generation, a 1U CubeSat, you could say, is roughly a 1-watt satellite. 3U CubeSats might have been up to about, let's say, 10 watts. And I'll talk a little bit more about this later, but 10 watts still puts you below the power envelope for doing a variety of, say, computational elements that are becoming now available. But when we get to that December 2010 launch, all of a sudden we have CubeSats that have over 50 watts of on-orbit average power. That's a big change, and it's really an enabling change. As an example, from the very beginning when we designed the CubeSat kit, one of the reasons why we chose sheet metal is because it allowed us to have a very thin wall thickness. So 100 by 100 millimeters, I wanted to run PC104 inside that. PC104 is 90 by 96 millimeters. So I've got 4 millimeters to play with between the outside dimension of my PC104, which is essentially a PC in a different form factor, and the outside dimension of the CubeSat as a whole. 4 millimeters, I got to split that 2 ways. There's a wall on the side that's 2 millimeters. I need tolerance as well. Now I'm down to, let's say, 1.5 millimeters. 1.5 millimeters is 60 thousandths wall thickness. That's an eminently doable in sheet metal, but I'm not going to be able to cut a 60 thousandths wall that's this long with any machine tool out there today, plunging in and coming in. So we approach that and say, hey, we really want to be able to see essentially PCs fly in space, and PC104 is a great form factor to do that. Now, nowadays, that has changed a lot. You've seen the Raspberry Pis, you've seen Beagle boards, you've seen Android phones. The cornucopia of Linux-type processors has expanded substantially since what was available back in 2000 or so. But PC104 still has a lot of argument going for it. It's essentially trivial to develop your entire satellite on a desktop with a bunch of Linux machines, whatever, and then essentially just take your software and put it in the boot of a PC104 and you're ready to fly. So what I was getting at there is that PC104, up until recently, was at least 10 watts minimum power requirement to run any sort of decent processor. There were some smaller processors that got declocked to lower power levels, but nowadays with something like an Atom, you're looking at a 1.6 gig Atom that runs at 5 watts, very reasonable power footprint, but it does require this greater available power that is now coming online. Another interesting problem in dealing with CubeSats, in fact, let me jump to this and I'll come back. This is the number, if you want to take any number away from dealing with CubeSats, I want you to remember this number. Apple's going to ship more than 100 million iPhones this year. They shipped about 60 million last year. In my opinion, the most interesting thing about CubeSat is that it is a platform that has allowed us to take advantage of developments in consumer technology unlike any other. LEO orbit is actually not that rough. The temperatures are pretty reasonable. You don't have huge radiation concerns. We want, in the CubeSat community, we want to take advantage of commercial technologies as much as possible. And let me tell you, whoever builds the parts for the iPhone must be really, really, really good in quality, much better than probably any space, anyone who provides components of the space thing. Because $100 million a year, the defect rate is vanishingly small. We want to take advantage of these technologies as much as we can. The trouble is, sometimes you can't take advantage of that in every way. As an example, there's a slide later, there's a program at NASA Ames to fly an Android phone. In fact, it's the first one, the Nexus S, right? The Nexus 1, whichever one the first of the Google phones is. And their concept was, hey, let's take a Google phone with Android in it, but it's got all sorts of things we want. It's got a camera, it's got rate sensors, it's got a magnetometer, it's got all these features inside it, and let's turn that into a brain of a satellite. I think it's a great idea because it's dirt cheap and it's got all this capability. It's probably pretty reliable. The problem is that it's physically just a little bit too big to stick into a Cubesat in a normal manner. And what they ended up having to do is stick the phone in the Cubesat on the diagonal, and as soon as you do the diagonal, oh man, the packaging is just brutal because you don't have the long dimensions that you'd like to play with. But they did actually come up with a design, we worked with them, where they are going to be flying this phone with, again, only a primary battery, just a whole bunch of lithium-ion cells that are pre-charged, and it'll have a lifetime of on the order of several days or something like that. And yet they're able to pull that off at very low cost. The phone itself is worth, what, maybe $500 at most. And yet, there are some technologies that we can't leverage for our Cubesats because they don't exist in the consumer realm. So one example is solar cells. So thinking, we want to leverage these low-cost technologies that are reliable, they're very cheap. They also deprecate very quickly. You take advantage of the fact that a new one comes along, it's got better features, it's got more memory, whatever. But there are also some areas that you can't really do that. As an example is space-grade solar cells with reasonable efficiency, say about 28% or so. They're available from not very many suppliers, and they don't come in very many form factors. So you play this interesting balancing game of trying to find components that have a physical dimensionality to them that work well in Cubesats, and at the same time trying to get something that is at a very high volume so that you can leverage the low price, the high reliability, etc. Another thing that's an interesting challenge in Cubesats is that, generally speaking, the Cubesat folks are not very rich. Michael, I look at you, and I know all the programs you've been trying to do. I know that, $60 million would change your life forever. Even $1 million would change things dramatically. But the limited budgets in the Cubesat realm are generally a lot smaller than that. And so what I see, certainly, if I wear my pumpkin hat, because I want to sell things sometimes, is that the limited budgets do mean the decisions that you make early on can have long-reaching implications. You might decide to build a Cubesat one way, and you find out fairly late on that the penalty that you're going to pay is that you have an enormous number of fasteners, for example. And a fasteners weigh half a kilo in a Cubesat that's going to weigh 4 kilos. So that's probably not a good way to do it, but you're so vested in that design that it's too late to change it. And lastly, we should point out that there are certainly some who view Cubesats as space debris. They're going up, they're causing some issues, they're right around, say, the orbits of the ISS. We don't want one of these things crashing into it. So there is a perception that Cubesats might actually be space debris. The response of the community then says, oh, sure, we're space debris, and we'll show you that either we will naturally deorbit within a short time period, or we'll even put a thruster on board so that we do deorbit within a short time period. So the community is very responsive to these kinds of things. But you have to have a good story. Just briefly touching on build versus buy, there are plenty of places that are capable of building something that is a Cubesat. There are others that perhaps are not. Somewhere in the middle, people will build some components and buy the others. I'd like to just touch on this right here. And this is an interesting problem that we on the commercial side have. When you're at a university, you have free labor, etc. It is rather difficult to compete against this when you say you have a group of students who feel, hey, we can build this thing and it'll get done in a quick time. The problem that we have as a community of commercial suppliers is that this tends to keep our market space down. It prevents us from having a larger market. And what's interesting is that if you think about, say, Apple and the iPhones and all that, in this community, we expect that kind of quality, that kind of performance, that kind of value. And yet, we are in a market that is involved in, say, maybe the building of 50 to 100 Cubesats a year, not 100 million units. So there's a bit of a disconnect there between what one can expect from the people who are supplying this market directly and what's available in terms of the commercial space. And of course, the challenge there from your standpoint, in terms of building, is to try to match as many of those different parts as possible, use as many of the consumer parts as possible, but where it's not possible, perhaps, go to one of the vendors who sell these things. And I should also point out that ARTAR is pretty brutal. I'm in a situation where my company is US-based. I'm a U.S. person, therefore I'm heavily constrained by ITAR. My foreign competitors are not. They make sure that they stay away from any sort of U.S. source materials. They therefore have potentially a larger market share or whatever. So this hurts us in the U.S., hoping that the recent suggested changes to the USML will improve our situation there. Again, I mentioned earlier that the Cubesats are very small, volume constrained. It's very interesting that Cubesat design is highly interdisciplinary. You really have to consider the entire system at all times, not just individual components. If you don't, very quickly some issues will bite you. I can think of several programs that are ongoing right now where they haven't addressed all the issues, and as a result they can have some issues, some problems. I'll just pick up one very minor one. On a Cubesat, you have, according to the standard, you have this thing called the access port. The access port is a port that is to be opened through the P-pod launcher so that, let's say, if your Cubesat is integrated in January, but you're only going to launch in, say, March or April, the overall standard would like it to be possible that, say, 2 months into sitting inside a Cubesat, you'd like to be able to jack in and perhaps recharge your batteries or whatever. So on the P-pod, the thing that this goes into, there are a couple of doors that can be removed with screws, and you can see that. All fine and dandy. There's, in fact, basically 3 areas where you can have an access port, the bottom, the middle, and the top. Once you add deployable panels in an effort to have more power on board, all of a sudden the panel has to carry that design detail with it as well. Still not a huge problem until you say, oh, but I want lots and lots of solar cells on my panels. Well, now what happens? Well, this is a case of a 6-cell panel, and there's, in fact, enough room to accommodate an end-based access panel there. If I go to 7, it gets really hard, and if I go to 8, it's impossible. Okay, so, I only have an access panel on one side. How about if I do 8s on all the other ones and 7s on this side? That's very reasonable, but your cost just went up, because now you're making 2 different products. You're making an 8-cell panel and a 7-cell panel. And your electrical power system may not actually be that happy with that. Your system might be tied to the notion that all of the string lengths should be roughly equivalent, and all of a sudden you have an 8 and a 7, you might not even be able to get power from this if you do a typical diode boring, and you're diode boring an 8 panel with a 7 panel where you're not getting power. So the flow through is pretty extreme in these small satellites, and you've got to, from a designer's perspective, you have to continually review all these kinds of incremental changes to make sure that they're not blowing up in some other place. As an example, there was a bus program called Kalman, which was driven by the NRO. Pumpkin built the satellites for that. This was basically a 1.5-page requirement specification that they gave us. We had quite a bit of leeway to design around. This is sort of a progression of Kalman 1 designs. Ultimately, they just wanted one thing. They wanted 1.5 liters of payload volume up here with the various other capabilities of the bus. The whole thing was done in about 7 weeks, I think. 2 of these have flown so far. If we had more time, we certainly would do it differently. And in fact, we have a successor bus to this that has a lot of new functions. But ultimately, what I thought was interesting from this entire process is to see how interdependent all these different components are. And in the end, I think part of our success there was that ultimately the bus was still relatively simple. It was not complex. There was not very much feature creep going on there. And we were only addressing the bus, not the total mission. Okay, real quick. Very important in this day and age, you're working in 3D CAD systems, your CAD has to be perfect in every single way. I just want to touch on these 2 things right here. 3D printing has become very popular in the past few years. Everybody has a Stratasys or a Uprint or whatever. This is a great resource to have. I strongly recommend any of you who don't have one either try to get one in-house or use printing services. And another very interesting and perhaps not completely obvious benefit from modeling absolutely everything is scale independence. And what I mean by that is I can zoom into any part of this model and verify that in fact I've got 2/1000 of an inch clearance in some area. which I could not do any other way. In fact, I can even illustrate it that way as well, whereas in our studio, there's no way I'm going to get any decent pictures of those kind of close tolerances. So definitely expect to have to invest heavily in your engineering team, your modeling team, in order to make sure that all of this stuff works together. On a larger scale, and satellite is this big, this is much less important. I mean, you certainly will use modeling for analysis and stuff like that, but on a smaller scale, this is absolutely mandatory. Quality matters. I'm just going to touch on this notion that I think that within, and this is beginning to tie, and I should preface it by this, we design everything at Pumpkin with the notion that we're going to build 1,000 of these things. I don't want to be building 1 or 10. Our minimum build these days is 25. If something goes up, 25 come back. It's not worth doing less than that. And I would like to see something goes out and 100 come back, and then somebody shows up and buys 100 or 1,000 or whatever. If we channel Apple's design methodology, whatever, I'm not a huge Apple fanboy, but I do respect some of their design decisions. I think it's very important to note that in order to have good quality, you have to have good design. And what this means is that you're iterating many, many times over a long time period to reach these kind of well thought out designs that fundamentally lead to quality. I have some pictures here. This is, for example, this is a Kalman bus. This is number 8, I guess. This is a Kalman bus inside a peapod that has just gone through shake testing. You can just see the long panels on the side. Here's that access port again. There were absolutely no changes made to this bus from the day we said go, when the CAD was finished, to when it was delivered to the customer. Zero, none. Everything was done in CAD land, and it turned out to have been done correctly. And it was all a function of that good design. And Adam and I had many arguments over many different features, but in the end we all settled that we felt that this was an adequate and correct way to do it, and in fact it worked out well. So very heavy feature on design. I tend to think of myself first and foremost as a designer. And the challenges that are presented by the Cubesat form factor continue to be really quite interesting to me. A little bit of talk about hardware and software. I'll give you a little story first. When we started, the Cubesat kit was designed around one processor, a TI processor called the MSP430. It's a very nice processor, very nice linear orthogonal architecture, very good on power, nice compilers, and all that sort of things. But I recognized that it was the height of arrogance for me to come in and meet with potential customers and tell them, look, you want to fly Cubesat, you better learn to use this processor. That's not the right way to do it. Frankly, I think that in many cases, the largest single piece of IT that Cubesat teams have is their software. And their software runs on some processor, and it's probably not on MSP430. So the approach that we took on our 4th generation was we were going to decouple the processor dependence of the architecture from the rest of the system. And as an example, when we did that Colony 1 program with the NRO, when we first met, I said, hey, what is the processor you want to fly? Yes, stop playing, guys. And they said, oh, well, we have a bunch of 8051s that have been in storage for like 20 years. And each time we fly a mission, we take 2 of them out, and we destructively test one, and the other one is the one that flies. I said, 8051s, really? Okay. All right, find me a modern 8051 you want to fly. And I worked with them, and we identified a particular 8051 from Silicon Labs. This is the C8051 airport plane. And at that point, we had the ability to essentially have pluggable processors, kind of like there's a socket on the motherboard. We could plug different processors into that socket and then flow through the entire bus. So we designed that processor with their help. We spun the processor board. The boards came in. I shipped a Cubesat kit to them, probably on a Friday afternoon. It arrived Monday morning, and by Monday at noon, they were running their entire code base. And they had never even seen our hardware before. So to me, I think it's very important. To me, it's always software that causes the schedule slips. Hardware, once your hardware is stable, you can just crank it out. And your only problem is finding the parts. And your parts may go obsolete very quickly, and then you're in big trouble. So you've got to buy big wheels of parts and keep them in storage. But software slips and all that, I can't deal with that. I don't like that. And I want to make it as easy as possible for the software elements to make their way into the satellite. So to me, I think it was very important that if you have an existing software code base, you need to be able to place that into a Cubesat with minimal effort. If it's Linux, it means you're going to be running on PC 104 or something like that. But I'll point out that there are subtle issues. Say, if you go to Linux, for example, there's a class of cameras, the GigE-Vision cameras. Those are gigabit Ethernet kind of link cameras. GigE-Vision is not an open standard. And I don't think this has changed. I don't think there's any GigE-Vision drivers outside of Red Hat and CentOS. So if you want to fly one of those cameras, you have to have a Linux distribution that's based on Red Hat or CentOS. You can't, for example, fly Debian. These are all issues that you've got to resolve fairly early on, and they will flow down to your hardware. The nice thing about it is that now with sufficient power, et cetera, pretty much the whole world of Linux computing is available now in Cubesats. And you should be able to come up with a platform that you will be able to fly. Again, just touching on this business of hardware obsolescence, currently there is one part of the Cubesat architecture that is in fact obsolete. I think we have a wheel of about 5,000 of them. There's only one for Cubesat right now. I don't particularly feel like changing the design, so they will last for a lot longer. But keep in mind that in terms of hardware design, it is very reasonable to think that what you design today will not be available 2 or 3 years from now, whether it's a phone, whether it's a particular memory chip, or whatever. So this is, you have to be very sensitive to this. Either build them all now, or stockpile them all now, or be prepared to change your design. Okay. So why is it that Cubesats drive tech innovation within the satellite community? Well, the thing that I really like about them is that you have very short development time frames, which means you have to ride the development wave. As an example, ferroelectric RAM is coming. It seems to be the savior for lots of our problems. In the case of Cubesats, because we are expected to be integrating new tech very quickly, because new tech is usually when it's pretty cheap and it's available, this allows the Cubesat community to take advantage of these things in ways that 5, 10, 15-year programs simply cannot do. We use mass-produced components. I pay no attention to lists of approved space materials or anything. I should say materials, but components. I use what we find or we think is going to work well, and we have not been proven wrong yet. But that's really because LEO is a relatively benign orbit. It's not that bad. Obviously, you take some effort to make sure that you have single event upset kind of mitigation strategies and all that. But there is no demonstrated need for rad-hard in LEO at this point. Everyone wants rad-hard. Everyone would like that, especially if we go interplanetary, whatever. We're going to need it. But at this point, doing a kind of LEO satellite, even LEO constellation, is capable of running these kinds of components. Also, it's interesting to note, and I think one of our next speakers will talk about this, the fact that the Cubesats are relatively low cost means that a launch failure or even another failure in a satellite is not a terrible thing. It means that you can probably rebuild the satellite and build another one relatively quickly and get it up there on orbit. And I mentioned the notion of dynamic responses to the problems. So let me talk a little bit about the trends in the hot topics. Right, just down here is a picture of that phone. You see it sitting diagonally inside one new Cubesat, a stack of batteries around it. I think at the bottom there's like a radio and such. But a very quick development cycle to get this thing into a Cubesat. That's it being balloon tested, and it will fly in August, I believe. Obviously, there's been a lot of talk about Earth imaging. DARPA had a call just recently called CME. It was a military application for Earth imaging, as well as space weather, talking about Android in particular because it's such an open architecture and because the phones have so many of the same components we would expect to have in the Cubesat. Power going up. This is a picture of one of our 56-watt arrays. Faster communications. There was a discussion about communication before. It used to be we're talking 1,200 bits per second, then 9,600 bits per second. There are 2 Cubesats right now that are flying about 1.5 megabits. And I think within a few years we'll see 10 megabits as a fairly standard, 10 megabits in S-band as a fairly standard common for Cubesats. Propulsion is coming. But again, I think that from my perspective, I'm not so much interested in what is the cool science experiment. I'm looking for what is the killer app. Because again, I'm looking for those large volumes of units that are built for the production train that's coming along, and people are just taking one off the line, throwing their science payload or their commercial payload into it and flying it. Okay, so that's kind of the first half of my talk.